Right, let's do this. We've got a quartic equation here with complex solutions, one of which is 2 plus I. We get another one for free. 2 minus I is also a root, because that's the complex conjugate. I'm not going to go into detail on where that comes from, but it's a fact that you need to be aware of. So if I want to express fz as a product of two quadratic factors, I can get my first quadratic factor from these. And it's going to be by doing, oh, I almost did x then, by doing z minus the root. Just like if you have a solution, if you have a root of 3, then x minus 3 would be a root. Here we've got a root of 2 plus I, so z minus 2 plus I is a root. And so is z minus 2 minus I. And these two multiplied together will give a quadratic factor. So I can multiply this out. I'm going to get z squared, cross multiplying, and I'm actually going to leave this inside the bracket. I think that will make life easier. I'm going to get 2 minus I times z. Then I'm going to get minus 2 plus I times z. I'm just doing cross multiplying. And finally, I'm going to get plus, because there's a double negative, 2 plus I, 2 minus I. Okay, let's simplify this. Z squared. I'm going to expand the brackets now. Minus 2z plus iz by getting rid of this one. Minus 2z minus iz by getting rid of the second bracket. And these can immediately cancel. Then I'm going to be left with plus 4. When I do 2 times 2, I'm going to get minus 2i and plus 2i. So they're going to cancel. I'm going to get minus I squared, which becomes plus 1. So I've not written all my working down for that, but it's going to give me z squared minus 4z plus 5. Okay, this is a one quadratic factor. So what to do with that now? Well, let's do a polynomial division. Hey, especially it says detailed reasoning, so we need to show where everything's coming from, and it's just good practice anyway. So I'm going to take this quartic and I'm going to divide by this quadratic. The method I'm going to do is, like, there are lots of different methods for this, but I like to just go for polynomial division, like a long division, essentially with polynomials. So z squared minus 4z plus 5 into 4z to the 4 minus 12z cubed plus 41z squared. Not loads of space for it, is it? Minus 128z. Okay, I might just need to move this along a bit. Sorry, didn't quite make enough space. Okay, that'll be alright. And then I've got plus 185. Going to make this work. Right. Z squared into 4z to the 4 is going to give me 4z squared. I like to write it above the column that goes with that. And then I'm not going into detail on how you do this, but like this is the process, and you multiply back through. Minus 4z times this is going to be minus 16z cubed. 5 times 4z squared is going to be plus 20z squared. Okay, subtract these. These cancel. Here, minus 12 minus minus 16, 4z cubed plus 21z squared, and bring this one down. Okay, then repeat. So z squared into 4z cubed is going to be plus 4z. Multiply This time we're going to get 37 z squared minus 148 z. Bring this down. Finally, let's see if this works. We've got z squared into 37z squared. That's going to be plus 37. Just need to check that we get 0 at the end, so multiply back through. Four times 37. If you double 37, you get 74. Double it again, you get 148, so it will be minus 148. 5 times 37 is 185. So brilliant, we get 0. And that's going to be our other quadratic factor, so quite a lot of effort, but we've got our answer. F, and this is going to be, you know, really help us for part B. But f of z is equal to this quadratic factor times this one. That's our answer to part A. Let's keep going. So part B. It's nicer because we just need to solve f of z equals 0, which essentially means we need to solve the, you know, if we can split these into the linear factors, we're sorted. We've already got 2 solutions. So actually we just need to solve 4z squared plus 4z plus 37 equals 0. Now it turns out this also has complex roots. It's not going to factorize with real like integers or anything, but we can get z. It does say we've got to show detailed reasoning. So z, let's do quadratic formula. Z is going to be minus 4 plus or minus 16 minus 4a. So that's going to be 16c. All over 8. Okay, do you know what? I'm going to carry on doing this without a calculator. So minus 14 plus or minus, now it's 1 lot of 16 minus 16 lots of 37. So actually it's going to be minus 36 times 16 square rooted. Oh, actually, it's just going to be easier to get my calculator out, to be fair. So 16 minus 16 times 37, which gives minus 576. It's going to change that. Okay, and it's going to be the square root of 576i, so 24i. Which will give me minus a half plus or minus 3i. So overall solutions. Z equals, let's do the ones right at the start. Remember what we had right at the start of the question: 2 minus I and 2 plus I. Minus a half plus 3i, or minus a half minus 3i. There we go. Okay, we're not done with this question because we've got the second part now involving loci. Just going to do a little screen grab and bring it down. two loci on an Argand diagram are defined by these sets. The set of Z such that the modulus of Z equals R1, and similar for R2. Now, what does this actually give? I think it's always worth sketching it. It's the modulus of Z is some constant radius, so it's going to be a circle centered at the origin. And then for the second one, we've got another circle centered at the origin. Now we've got that R1 is greater than R2, so let's say that this here is R1 and this here is R2. I could draw an arrow on to show the radius. It's like going to be the radius throughout the circle, but I'm just going to give sort of the X value at this point. We're then given that two of the points from the solutions to before are on C1 and 2 are on C2. So we need to think about which ones it is, and we can do that by finding the modulus essentially. If we find the modulus of 2 plus I, we're going to use Pythagoras' theorem, because the modulus is like the distance. Let me just quickly talk about it. It's the distance from the origin to the point. So I can use Pythagoras to do 2 squared plus 1 squared, because I'm just talking about an Argand diagram, the lengths, and we're going to get root 5. And that's going to lie on one of the circles. Then we've got the other one. We've got, let's go with minus a half plus 3i. Put it down here. In a similar way, that's going to be a half squared plus 3 squared square rooted, which is going to be 9 1/4, because I've got 9, I've got a quarter, square root of 9 1/4. Or as an improper fraction, that's going to be 9 times 4 is 36. It's going to be 37/4, all square rooted. To be fair, it's probably easiest to leave it as a mixed number, but I can see that this one is bigger. So my minus a half plus, so this complex, let me these two complex numbers are going to be on the outer circle somewhere on this one, and then the other two are going to be on the inner circle. But what we've just shown, in fact, is that this root 5 is in fact going to be it's going to be R2. It's going to be the radius of the smaller circle, and then this here is going to be the radius of the bigger circle. So if I want the area of R, R is the region between C1 and C2. It's going to be this bit here. It's going to be pi times, I'm going to stick with 9 1/4. Pi times the root of 9 1/4 squared, which is just 9 1/4, minus pi times root 5 squared, which is just 5. So I'm going to get 4.25. I'm going to write it as a decimal now, pi. And that's my exact answer. Finally, we're told that omega is the sum of all of the roots. Determine whether or not the point on the Argand diagram which represents omega lies in R. Is it somewhere in this purple region? Okay. There's two ways to do this question. First way, probably the one that I kind of found most intuitive, is to actually take the roots that we've got. We've got 2, I've already forgotten to be fair. We've got 2 minus I plus 2 plus I. Hey, the i's are going to cancel, brilliant. Plus minus a half plus 3i plus minus a half minus 3i. The 3i's are going to cancel. That's going to give me 4 minus 1 which is equal to 3. Second way, which is a bit quicker, but you have to kind of remember it, is to go all the way back to the start of the question. And remember, when you got a quartic, if you sum your roots, sum alpha, then you get minus b over a, which in this case is minus 12 over 4, which again gives 3. So you could do it that way instead, but I reckon this way is a good shout. It didn't take that long. So basically, omega is 3, and the question is it like in here? Is it in here? Remember, I'm putting it along the real axis, or is it outside? Well, we can compare it with the radius, the radii, I should say, and we can see that it's, you could even write it as root 9. That's probably the best thing to do, because then we can compare more directly with the square roots. Because we've got the first radius was root 5, and root 9 is bigger than that. However, it's going to be less than root 9¼ So omega lies, what did it say exactly? Lies in R. Brilliant.